So we're given the function f of x equals 3 to the x. And we want to answer our first question, which is to explain how we know that this function has an inverse. Well, how do you determine if a function has an inverse? You need to see if it's 1-to-1. So I'm going to go ahead and take a look at its graph, f of x equals 3 to the x. This is an exponential function. And the question is it 1-to-1? Does it pass the horizontal line test? You look at any horizontal line, like for example, y equals 2, and it cuts the graph in 1 point. A function fails the horizontal line test if a horizontal line cuts in more than 1 point. But you can see any one you use, right? Any horizontal line you use is only going to cut the graph in 1 point. Therefore, it is 1-to-1. So since the graph is 1-to-1, we can say, since the graph passes the horizontal line test, it is a 1-to-1 function. Therefore, it must have an inverse. Now, we want to graph those. We've graphed y equals f of x, and how am I going to graph f inverse of x? Well, let's take a look at f of x first here. So I want x, and I want f of x equals 3 to the x. If x is 0, 3 to the 0 is 1. If x is 1, 3 to the 1 is 3. If x is 2, 3 to the 2 is 9. 3 to the 3 would be 27. That'll be difficult for us. Let's see, how about 3 to the negative 1? That's 1 over 3 to the first, which is 1/3. 3 to the negative 2. 1 over 3 squared, which is 1/9. And 3 to the negative 3. 1 over 3 cubed, which is 1/27. So those are points on f of x. To get f inverse of x, of course, we know we switch x and y. So what was x becomes y. What was y becomes x. So we had 0, 1. This now becomes 1, 0. We had 1, 3 becomes 3, 1. We had 2, 9 becomes 9, 2. We had negative 1 1/3 becomes 1/3 negative 1. We have negative 2 1/9 becomes 1/9 negative 2. We have negative 3 27 becomes 1/27 negative 3. So let's go ahead and graph all of those points on Desmos so we can see the function of f of x and the function of f inverse of x. So again, those points are 1, 0, 3, 1, 9, 2, 1/3 negative 1, 1/9 negative 2, and 1/27 negative 3. So you can see where this is heading, asymptoting this way, growing that way. It is a reflection through the line y equals x, yes? And remember, this function was y equals 3 to the x, so the inverse would be x equals 3 to the y. I mean, that's one way for us to answer it, right? But let's see if we can express it in function form. That's not quite in function form. So what we have here is we have f of x equals 3 to the x. Which of course means y equals 3 to the x. We want to find f inverse of x. How do we do that? X becomes y, y becomes x. So that's x equals 3 to the y, which is again what we did on Desmos. But now to get it in function form, I want to solve for y. Well, what am I going to do? I could take log base 3 of both sides. Or I could take natural log or log base 10 of both sides. But log base 3 has an advantage, as you'll see here shortly. So I get log base 3 of x equals, we can pull the exponent down, y times log base 3 of 3. But what is log base 3 of 3? Log base 3 of 3 equals what? 3 to what power equals 3? Well, 3 to what power equals 3 to the first just equals 1. So log base 3 of 3 is 1. So I get log 3 of x is y times 1. So y equals log 3 of x, log base 3 of x. Y is, of course, f inverse of x. So we've determined what f inverse of x is. The inverse of 3 to the x is log base 3 of x. That, in essence, is our definition of the logarithmic function. So if we go back to Desmos, if I want to graph log base 3 of x, let me go ahead and turn this one off for a minute and say y equals log base, shift underline, log base 3 of x. We hope it's going to go through those points, and it does. And you can see that the original function f of x equals 3 to the x, and the inverse function f inverse of x is log base 3 of x, are mirror images across the line y equals x.